Now we will assume for our analysis that the damping coefficient C is greater than 0. For mechanical systems, this is almost always the case. This assumption will lead us to solutions that are dissipative in nature. In other words, the amplitude of the vibration response will decay over time. Now, in the full analysis of oscillators with viscous damping, you'll note that there's different types of solutions depending on the value of the viscous damping coefficient. For the purpose of this review, we won't go into all of those solutions. We'll just concentrate on the ones that will be most relevant to work that we will be doing. If we were to solve the differential equation completely, we would note that there's a critical value of damping, which we call C critical, in which the solution transitions from an oscillatory response with decaying amplitude to an exponentially decaying response that does not oscillate. This transition occurs when C is greater than the critical value, which in the solution of the differential equation is found to be 2 times the square root of Km. Now, for the sake of this review, we will concern ourselves with one of the 3 cases associated with the solution of the differential equation. The case that will concern us the most is the case which is called underdamped motion, and this occurs when the value of the damping coefficient C is smaller than the critical value C critical. In the case of underdamped motion, the free response is a harmonic function whose amplitude decays with time, and as we'll see, the rate of decay of the amplitude is a function of the damping coefficient C. Solving the equation of motion in the underdamped case, the expression for the free response is found to be x of t is equal to a, amplitude, times a function e to the minus zeta omega sub n t, times a harmonic function which has an argument of omega sub d, t plus phi. Now the 2 new terms in this response are zeta and omega sub d. Zeta is the damping ratio, and it's a non-dimensional parameter which is defined as the damping coefficient divided by 2m times the natural frequency. And the damped natural frequency, omega sub d, is equal to the undamped natural frequency, omega sub n, times the square root of 1 minus zeta squared. In the case of underdamped motion, the value of the damping ratio is bounded by 0 and 1. The case when zeta equals 1 is called critically damped motion. In the case of zeta equals 0 is the equivalent of undamped motion. Note that the solution for the free response of an oscillator with viscous damping reduces to the solution of an undamped oscillator when zeta equals. Let's take a moment and look at representative time responses of an oscillator with viscous damping. The values of the parameters are shown in the top right of the plot. In this case, the damping ratio zeta is chosen to be 0.35. As the plot demonstrates, the amplitude of the free response decays with time. The red dashed line is the decay envelope A e to the minus zeta omega nt. This decay envelope bounds the oscillatory motion. Changing the value of zeta changes the decay envelope and results in a response that oscillates longer. In this plot, we reduce the damping ratio to 0.05, and as you can see, the decay envelope is longer, resulting in a larger number of oscillations. If we let the simulation run for longer periods of time, the free response would eventually decay towards 0, just as we showed in the plot with a larger value of zeta.